Okay, so this is an optional video on instantaneous velocity examples. It's not required viewing. If you would like to see a couple of worked out solutions to some problems that you might see in your homework, this video is for you. Now, there are two different kinds of problems here. One of them is just a general problem that's doing some graphical analysis. The other one will involve a little bit of calculus, so feel free to watch whichever you'd like. Problem 2-9, this is from my calculus-based physics book, but there is no calculus here, it's just graphical analysis. The position of a rabbit along a straight tunnel is plotted to the right. What is the instantaneous velocity at 10 seconds, 30 seconds? What is the average velocity between 0 and 5 seconds, between 25 and 30 seconds, and between 40 and 50 seconds? So it's going to be a lot of graphical analysis. Remember now, the bunny rabbit is not moving along a hill here, right? You might think of this as moving along some sort of two-dimensional hill. It's not the case. Remember, the rabbit is restricted to move in 1D for this chapter. So this is merely plotting x as a function of time. And so the bunny is just simply moving to the right or to the left. Let's take a look at letter A. What is the instantaneous velocity right at this point? Now, I don't really have to construct a slope of a line tangent to the curve. I see that that's pretty similar to what the average velocity is over quite a length of time. I'm going to go ahead and run this thing out to about here and say that, you know what, if I can get the slope of that line, then I can go ahead and determine the instantaneous velocity at 10 seconds just by taking that value. So I'm just going to drop some lines down here. You typically do this in your math classes. And to be able to get that slope, let's go ahead and put some numbers in there. Let's see, that looks like a change of 5 meters. That's my displacement, and that takes about 18 seconds. So if I were to say for letter A, the instantaneous velocity is equal to the average over this 18-second time interval. And that's just delta x over delta t. Looks like they change, the red bunny changes its position by 5 meters to the right. It takes 18 seconds to do that. And so when I take 5 over 18, I get about 0.28 meters per second. Okay, so quite easily done. Letter B, what is the instantaneous velocity at 30 seconds? Let's switch colors here. So at 30 seconds, I employ a similar technique. Because I got somewhat of a curved line here, I'm going to use a line tool here. And so see if I can't get a line that sort of goes between here, and try to find some convenient points that I can determine that slope. So I'm going to try it right around there. Again, without having the actual position written as a function of time, I can't employ any of those like calculus tools here. This is just a graphical approach to doing this. So let's go ahead and okay. So much easier to do on actual pencil and paper. Let's see if I can do this. There we go. And when I look at this, it looks like a rise of 10 to 20, I'm going to say 23. This is a rise of 13 meters. And it looks like a run of, made that easy, about 10 seconds. So for letter B, the instantaneous velocity, at least approximately, is the slope of that line. And so I'm going to say that that is 13 meters over 10 seconds, or about 1.3 meters per second. And that is at a time of 30 seconds. Okay, so that's an instantaneous value. Okay, letter C, what is the average velocity between 0 and 5 seconds? You know what, I'm just going to go back to orange. And the reason for that, for letter C, is because we already determined the average velocity between an 18-second time interval. Well, that'd be no different than what it is between 0 and 5. So I'm going to switch that to average velocity. That's specifically what it's asking for. We calculated before, 0.28 meters per second. And again, you might not agree exactly with these numbers because of these graphical approaches, but nonetheless, we should be pretty close. Letter D, between 25 and 30 seconds. Go ahead and switch colors again. 25 and 30. So that is from around here to here. You get the idea here. So I'm just going to do this to try to get us an answer fairly quickly. I'm going to get that change in position there to be, looks like maybe that's maybe 9 up to 16. So I'm just going to say that 9 to 16 is 7 meters, and that time is set at 5 seconds. So for this one, I'd say for letter D, the average velocity would just be the slope of that line, which would just be 7 meters in 5 seconds, which is just about 1.4 meters per second. Let's do a quick little quality check. These are near the same point along the graph. This is at 30 seconds. This is between 25 and 30. When I look at those two lines, I can see that the second one I constructed is a little bit steeper than the other. So maybe in the beginning, you can certainly tell by looking at the general shape of that graph that it has a little bit more of a steeper slope in the beginning, and then is shallowing out a little bit over here. So yeah, that seems to make sense. It's a good little quality check to make sure I haven't made any math mistakes, which is common. We will often make math mistakes when we start doing graphical analysis, and that's okay. Between 40 and 50 seconds. Now we're way over here, and let's see. Let's go with yellow. Between 40 and 50 seconds. It's an average velocity, so I'm just going to construct a line there. You get the general idea. This is set to be 10 seconds, and it looks like it's got a rise. Remember, now this is actually a fall of about 10 meters, so the bunny comes back about 10 meters from there. If I were to get the average velocity, a little bar over that, between 40 and 50 seconds, it would be a negative 10 meters in 10 seconds, or about -1 meter per second. Sig figs are sort of hard to do graphically. You just sort of have to estimate whether or not you can go with an extra digit there or not, but that's okay. This gives us a sense of how to apply the instantaneous velocity values. Okay, now this next one is a calculus-based problem. This is from my AP Physics book, and this one does involve some calculus. So if you are in general physics, and you don't need to watch this one. But if you are in general physics and you've had some calculus, feel free to take a look at it. The position of a small object is given by this x as a function of time expression that we have there, where t is in seconds, x is in meters. Plot x as a function of time from 0 to 3 seconds. Find the average velocity of the object between 0 and 3. And then at what time between 0 and 3 seconds is the instantaneous velocity equal to 0? Truth to be told, the first two parts of this problem just involve general math principles, so you don't need to have calculus to do this. Letter C would involve some calculus, so let's take a look at it. First thing I'm going to do, and this is not a math class, you probably have done a fair amount of this in math before, so I don't want to go through all of that process. I just created a quick little t-chart and got a x as a function of time table here, and then I can go ahead and graph that. If you have a graphing calculator, you could certainly do that as well. I'm going to pull out what that graph looks like when I plot those points. And so sure enough, it's a cubic, right? You can see it's a cubic and it's got a negative out there, so you should see that the general shape of that graph would end up being something like this, right? You should be able to identify general shapes from your understanding of what the general form of that equation is. Let's go ahead and just sort of draw that in here. Of course, it continues on in both of these directions. So looks like it's it's got a general shape on the far to the left and far to the right of the origin, but around the origin it goes through some convoluted mess there. So let's see. Plot x, no problem. Find letter B. Find the average velocity object between 0 and 3 seconds. Well, there we go. It's not too bad. Average velocity for between 0 and 3. I'm just going to determine now the slope of that line. And again, you can see that definitely this motion is quite a bit more complicated than just going from point A to point B. So we're missing out a lot of the nuances in here, but we can get an average over that time interval simply by taking the slope of that line. I see a rise. I'm going to look at my data table for that. I'm going between 0 and 3 seconds. So my rise is actually 10 minus 34. Right? Order of subtraction is important. So I ended at 10 meters, I started at 34. And that time interval was 3 seconds. And so it would be negative 24 meters in 3 seconds. And sure enough, negative 8 meters per second. Letter C, last problem for this video. At what time between 0 and 3 seconds is the instantaneous velocity equal to 0? Now, in your calc class, you probably know that the reason we take derivatives oftentimes is we like to know where the slope is equal to 0, right? Where the slope of a line tangent to the curve is equal to 0. Here, if I were to take a slope of a line tangent to the curve and find where that slope is in fact 0, that means there is 0 rate of change of position at that point in time. That's around here, right? So I'm going to try to find whatever that point in time is. Maybe right around there. I'm not sure exactly where it is, but calculus allows us to do that. So I'm going to take the, I already have x as a function of time. I'm going to rewrite that here. If I were to find the instantaneous velocity, we know that that is the derivative of x, x as a function of time. I get, let's see, the derivative of 34 with respect to time is 0. 10t would be 10, and then minus 6t squared. You'll find that the calculus that we have to do in physics is actually fairly straightforward and not too bad. If you're new to calculus right now, this might be confusing. You'll see that ask any student that's been through calculus, this is fairly bread and butter kind of material, and so you'll become an expert at that before too long. Now, I'm going to set that equal to 0 because that's what the question is asking. At what time between 0 and 3 seconds is the instantaneous velocity equal to 0? So I set that equal to 0, solve it for time. I get 10 is equal to 6t squared. 10/6 is equal to t squared. I can reduce that to 5/3 if I wanted to, but ultimately I'm just going to take the square root. And when I'm done, I get this value. About 1.29, 1.3 seconds. Okay, and that seems to match my graph. If I come over here, 1.3 seconds, somewhere around there is the point at which the object has an instantaneous velocity equal to 0. It happens to be the point at which the object changes its direction of motion as well. Okay, so there we go. I'm going to go ahead and stop this video here. I hope you found these problems useful.